Hey guys, welcome back to Genius Learning. All right, so I saw this problem on an exam recently, and I mean, it just looks spooky. It just looks like it has a lot going on, and I thought I'd show you guys, see if we could break it down and make sense of it. So we have this drawing up here, right? A table, we got two pulleys, and we got a mass connected by a rope to one side with another mass hanging. And on the right side, we got another mass hanging. So 3 different masses, right? We have this table and we're given that M3, so this one, is greater than M2 and M2 is greater than M1. So the system is actually going to the right, right? This M1 is going upward, this M2 is going towards the right, and this M3 is going down. Now, they don't tell you this in the problem, right? The accelerations. But you have to gather that from this, which they do give you. Okay, so where the system is accelerating. Now, it says find the acceleration of the system, okay? The good thing about this problem is that they don't give you numbers. So what we have to find is an equation that has acceleration equal to, values or these terms right here. And we don't have to actually put numbers in, right? So you just have to derive what it would be if they gave you the numbers. So we'll see what that means now. Okay, so find the acceleration of the system. First of all, we have these 3 different boxes, right? And we need to do a free body diagram, right? Or a force diagram on each one, okay? So this is gonna take us back to the sum of forces, which we did, a couple videos ago. So let's do free body diagram for each box. That's kind of always what you want to start with, right? You have this three-piece system. We're going to do a free body diagram of each one to see what the forces are on each mass. Okay, so I guess let's keep the colors how they are, right? So let's do, actually looks a little bluish. Okay, so M1, right? The one that's hanging here. Let's do so I'm going to label this free body diagram. Okay, this is for that's right here, M1, right? Now you have tension in the rope going upward, right? So there is tension, and I'm going to label that tension 1, right? Because that's coming from mass 1. So tension 1, and then downward always we have mass times gravity. Now remember, all the masses are different, so we got to put mass 1 times gravity, right? And that's the only forces being applied because it's not, moving left or right. So we only got vertical, okay? Now, right when we do the free body diagram, right, let's just do the sum of forces right next to it. So everything is neat, okay? So now we have the free body diagram of the first thing, and now let's do the sum of forces. Okay, so the sum of forces, which was the sum of forces equals MA, right? So F equals MA, right? And remember that we need to do it for the X direction and the sum of forces in the Y direction, both of them, okay? So sum of forces in the X, well, clearly there's no forces in the X because it's only in the vertical direction. So this is 0. Now we have forces in the Y. Okay, so we know that going upward, or we're gonna put that going upward is positive, right? Positive Y. Going downward is negative Y. So tension is in the positive direction. So for forces in the Y, right, I have positive tension, so T1, minus M1G, that's going down, equals, so we have our force, right? And now it equals MA. But remember, it's M1A because that's what we're talking about. So F, which is our forces on the box, equals MA. Boom. Okay. So I'm going to rearrange this one to solve for T1 now, so it's a little easier. So let me just do that real quick, and I'll do it in pink, I guess. So I'm gonna put this on the other side, right? So I'm gonna have T1 is equal to M1A, that stays there, and then this is positive on the other side, so M1G. Okay, so I'm just solving this one here for T1, so that way I could already have it ready for what I'm gonna need later. So I'm gonna put a little Roman numeral 1 next to that. Okay, so now let's do, so we did free body diagram for the first one, and we did the sum of forces for the first one. Okay, we got this equation out of it. Now let's do the second box, which is in the middle, the second mass, and let's apply the free body diagram. So now we're gonna do free body diagram of mass 2. Okay, so mass 2, let's first start with, it's sitting on the table, right? And we know that the normal force is always up, perpendicular, right, to the surface. So that's normal force, right? We know that mg is always pointing downward, right? And since the masses are different, this is m2g. Okay, perfect. So that's in the y direction. Okay, now in the problem, I should mention, in the problem it says that we do have friction. Okay, so sorry about that. You know, besides find the acceleration of the system, it says that the table does have friction. So we're going to apply the friction in the horizontal direction. So the y direction is taken care of. Now let's look at the horizontal direction. All right, what do we have? We have tension in this rope, right? It's being pulled by this one because it's going in this direction. So tension by, and we're going to label this tension of T2, right? Because this is the, you know, rope coming out of mass 2. We have tension T1, right? This is tension from 1, right, being pulled. So it has to pull it, and it's being pulled. There's a tension in the left direction. And remember that the system is going this way, okay? So friction always opposes motion, always opposite to motion. I mean, think about it. Whenever something is rolling or whatever, we're going in a certain direction, right? What's slowing us down is friction, which is acting in the opposite direction, right? Which what slows the ball down from rolling, or your wheels when you're driving, you know, the friction. So friction is going to be, let's put it in a different color. Friction is going to be to the left, and that's kinetic friction, right? Because it's moving. So tension in the rope, tension from the other mass. We got friction opposing the motion because this thing is going to the right. We got normal, and we got mg. So that's all the forces that are being applied on box 2, right? And now let's do the sum of forces, right? And so again, we need to do the sum of forces equals ma. Okay, we got to do the sum of forces in the x direction, okay, and we got to do the sum of forces in the y. So let's just start with the x first. Okay, we have tension 2, which is positive, right? We're gonna say that to the right is positive, to the left is negative. Okay, so T2 is positive, so T2, right? Then we got T1, which is negative, so minus T1. And we also have minus kinetic friction, so frictional force, right? Kinetic frictional force equals ma, right? And since we're talking about box 2, this is m2a, right? So these are the forces being applied in the horizontal. Force equals ma. So this is one equation, right? And we're just gonna hold on to this one like that, since we have 2 different t's in it. And we got the sum of forces in the y, right? And what do we have in the y? We have the normal, and we have mg. Okay, so we said that upward is positive y. So we got normal is positive, minus m2g, that's the forces, and equals, now remember y the mass acceleration, or rather the acceleration in the y, is equal to 0. Because this box, as it's moving across the table, is not going up and down in the y direction, right? It's not bouncing up and down. It's not crushing into the table. It's not, going like this. It's going flat. So in the y direction, there's no acceleration. There's only acceleration in the x. So that's why this part of it, acceleration in the y, is 0. So we're going to move this over, and we're going to have n is equal to m2 gravity. Okay, so we're going to hold on to this, and we're going to hold on to this one, just like we held on to the Roman numeral 1 there. So let's put here Roman numeral 2 around this one, and Roman numeral 3 around this one. Okay, so perfect. We have, let's separate. So we did, let's see. Now let's do the third box. Okay, so you see how we did free body diagram, free body diagram. We're gonna do free body diagram for the last one. And let's do it in green. Okay, so we have here, let's see, free body diagram, right? M3. Right now, what forces are being applied to this box here? Well, we have tension, T2 going upward, right, from the rope, right? The classic mg going down, right? But since this is M3, we got put M3G. So we got those two things. There's no horizontal forces because it's hanging off the table. So we're good there. And now let's do the sum of forces, okay? Sum of forces is, the sum of forces equals MA, right? Remember, the summation sign means we want sum of forces from the x direction and sum of forces from the y direction. Okay, since we don't have any forces in the x, this part is 0, and the forces in the y are going to be tension going up, right? T2, which is positive, minus M3G, right, because that's going downward, equals, now this one also we have to watch out for, okay? We're going to put minus M3A, okay, and I'll tell you why right now. So in the first box, you notice how we have the kind of like the same situation, right? Where we have a hanging mass, okay? And in the hanging mass one, for the first one, we put, T minus mg equals ma, regular positive acceleration. And then for this one, for this last one now, we have the similar situation, positive T2 minus m3 equals negative mass acceleration. This negative is due to the acceleration direction, okay? For this box right here, since the system is accelerating this way, right? This is the heaviest, so it's pulling down, this one, then this one. This acceleration is going upward, which is the positive y direction. So it stays positive up here. But when we're talking about this box right here, it's going downward, and the acceleration downward is negative. Okay, so the acceleration here is positive because it's going up. Acceleration here is negative. That's what changes this. This is key. This right here is, the third mistake. If you get this far, this is the biggest trick of the whole problem. Okay, so this is definitely something to look out for. This negative sign right here, that'll throw things off completely. All right, so we have that, right? Let's solve for this T2 because it's the only T there. So let's rearrange it and make it look nice. So we have T2, right? And if I put this on the other side, I will have a positive M3G minus M3A. Okay, and let's hold on to that. We're gonna say this is Roman numeral 4. I think that's 4. Okay, so this is the process, right? We got free body diagrams, we got sum of forces. Free body diagram, sum of forces, free body diagram, sum of forces for each mass. That's how we're gonna solve this problem. Now we can answer the question, what is the acceleration, right? Find the acceleration of the system. Okay, so let's take these equations that we have in pink and let's use them now to solve for acceleration. All right, I'm gonna put this here. Let's see, kind of blocking a little bit. Let's see if we have room to put both. All right, so let's do it like that. Okay, so let's do both. Let's do that. Now we have 1, 2, 3, 4. Okay, we're gonna use those 4 equations to solve for acceleration. All right, one thing we also need to remember is that formula for friction here. So a little side note. So this right here, so note, this is a formula. So kinetic friction, right? Kinetic frictional force is equal to the coefficient of friction times the normal. So this is the coefficient, this is the frictional force. So if they're asking you for frictional force, you have to give them this number, right? Which is a combination of the coefficient of friction and the normal. And now, I'll explain now what all that means. All right, so we need acceleration, okay? And out of these 4 equations, this one here includes T2 and T1, right? This one only has T1, this one only has T2, and this one doesn't have either one. So we're gonna look at this equation here. So let's look at equation 2 that we got from our sum of forces. We got T2 minus T1 minus frictional force, kinetic frictional force, equals M2A, okay? Now, we know what T2 is because we got it on equation 4, right? We have a whole, T2 equals a bunch of stuff, and we know T1 is equal to a bunch of stuff. Well, this bunch of stuff has the variable that we need in it. It has A, and so does T2. All this has an A in it. So let's change T2 for this, and let's change T1 for this, okay? And then we'll continue like that. So let's do this. T2, right, I'm gonna start with T2. Instead of writing T2, I'm gonna write this whole thing here. So I'm gonna write M3G minus M3A. Okay, that is just for T2. Then I'm gonna put minus, and let's do T1, which we got in the first sum of forces, which is equal to M1A plus M1G. Boom. Okay, minus friction, kinetic frictional force equals M2A. All right, now let's change this frictional force to the equation that we have, okay? So I'm gonna rewrite all of this, except I'm gonna distribute this negative, which is a big mistake algebraically that a lot of people make, right? Make sure that this came with parentheses, and we gotta distribute this negative into both of these, right? So this part I'm gonna keep the same, so M3G minus M3A, distribute this in, that's minus M1A, distribute that into that one, minus M1G. Perfect. Now we're done with the 2 pink parts. Minus frictional force, I'm gonna put mu, right, mu K, right, coefficient of friction, times N, and then finally we have M2A. Okay, so everything here looks good. We need acceleration. We're gonna solve for that. We know gravity, remember we don't have any numbers for these, but we need to have it in its simplest form. This is not in its simplest form because in the problem, they'll give you coefficient of friction and things like that. This right here, the normal, we have an equation that has normal is equal to mass 2 times gravity, which is perfect. So let's use the third one, right, which we didn't use so far, and let's plug that into here. So again, I'm gonna rewrite this, and now I'm gonna put the value of n as m2g. So I have m3g minus m3a. This, I'm just repeating this entire part, so I'm not doing anything over here. Okay, now I'm gonna put coefficient of kinetic friction, mu, times the normal, and the normal we derived from these four equations. One of them has normal in it. So I'm gonna put m2g equals m2a. So if you think about it, you have mass 2, you have mass 1, and you have mass 3. So everything is included in this equation, right? And it needs to be, because the acceleration needs to be from the entire system. So now we have this, right? And this is great because now all we have to do is separate the a's on one side and everything else on the other side, right? We're solving for acceleration. So let's take this acceleration term, or better, let's take these two acceleration terms and put them on this side of the equation, right? So I'm gonna take this one and this one, put them on the other side of the equation. So I'm gonna have m2a, right? I'm gonna have this positive m3a, this positive plus m1a, right? Because they went to the other side. And these three things stayed. So this stayed there, which is m3g minus m1g minus coefficient of friction m2g. Right? I put everything kind of backwards, but I put these on the other side of the equation, which makes them positive, so everything's positive. These three things stayed. And that's it. So now what we got to do is take out all the a's from this side, right? Because we want to solve for acceleration. So acceleration now is taken out, and we have m2 plus m3 plus m1, which looks nice already. Everything here stays. m3g minus m1g minus mu coefficient of kinetic friction times mass 2 times g, right? And we're gonna pass this whole thing in parentheses underneath here to solve for a, right? I'm also gonna take out the g to make it look a little neater, but let's do it in parts. So a is equal to, I'm gonna keep this whole thing there, right? Because I'm gonna divide this to the bottom. So this whole thing I'm keeping, but I'm gonna take g out of everything. So I'm gonna put m3 minus m1 minus mu k m2 close parentheses, all of that times g, right? Because each term had g, I pulled it out, and then I just wrote the inside, divided by all of this. So we got m1 plus m2 plus m3, and that's it. This is our equation with acceleration in it. Okay, so the basic idea is to understand when you have a system with more than one mass, even if it's one mass, we do the free body diagram, right? That's the first thing we should think. You have to establish where your coordinate system is, y and x. Where is it accelerating towards, right? Because that's going to be important. And first things first, free body diagram. What are the forces being applied on that object individually, right? This was individual, and this too. Then once you do the free body diagram, we do the sum of forces, right? The sum of forces in the x and in the y. The x and the y, x and the y. Some of them will be 0. Other ones you have to understand that the acceleration is 0 because it's not, jumping up and down. And some of them you have to understand if they're accelerating in the negative direction, the MA part at the end is going to be negative, right? Different from just regular MA. Once you have that, circle or kind of highlight the equations that we got out of the sum of forces and use them. These are going to be the things that you use to solve everything. And so we have a frictional force, coefficient of friction, the normal is the equation you should know. And we take one of the equations that we got and we plug things in and we go, you know, massaging it a little bit until we get acceleration equal to whatever, you know, all these values. They can give us the coefficient of friction in the problem. They can give us all three masses in the problem, like numbers. We know gravity. And so once we have those three things, that's it, you know, just four things. We'll be able to get a number for this. Okay, so right now it's just the idea of how to approach this. And you know, it definitely looks like a harder problem than what it is. Very spooky at first sight, but I think that breaking it down, it's and going through it a little slower, you'll see that it's just systematic. You know, it's just do the same things over and over. Be careful with your algebra, and you know, make sure you do the free body diagrams first. Okay, I hope this helps, guys.